Hello everyone and welcome. This is General Chemistry 2, lecture number 11. Here we're going to introduce the topic of equilibrium. We're going to learn about equilibrium concepts and constants. This covers OpenStax sections 13.1 and 13.2. First, what is equilibrium? So contrary to what you have learned up to this point in chemistry, most chemical reactions are actually reversible, right? Typically, when we think of writing chemical reactions, we write them with that forward only arrow to denote the conversion from reactants to products, but most reactions are reversible. They can run in both directions as noted here by the double arrows. So considering this reaction, N2O4 to form 2NO2, the double arrow here shows that N2O4 can break down to form two NO2 molecules, but these two NO2 molecules can also combine and go run back in this direction to form N2O4. So a double arrow indicates that the reaction is reversible. It can run in both the forward and reverse directions. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and this is very important. This is something we mentioned briefly towards the end of lecture 9 when we were learning about reaction mechanisms and the concept of kinetics. So again, we generally could call this like a dynamic equilibrium. It's important to note again that at equilibrium, it's the rates of the reactions that are equal to one another. It's the rate of the forward reaction would be equal to the rate of the reverse reaction. So once equilibrium is reached, neither concentration changes. So again, to restate this one more time and be completely clear here, equilibrium does not mean that the concentration is equal. When equilibrium is reached, that does not mean that there is an equal amount of both the reactant and the products. There will be different amounts, and we will see how we can define and determine the amounts present. All equilibrium means is simply the rate of the forward and reverse reaction are equal to one another. So for reversible reactions, all roads lead to equilibrium. Doesn't matter what you start with, you will eventually reach equilibrium. So here we're showing the reaction 2SO2 plus O2 to form 2SO3. We can see this is a reversible reaction. SO2 is labeled in green, O2 in red, and the SO3 in yellow. If you were to start with only reactants, so some amount of SO2 and some amount of O2, we can see that they both decrease over time. The rates of the decrease are different because of their coefficients, so a little shout out to the kinetics lecture there. And then we can see SO3, it increases as the product is formed, but eventually the decreases and the increases level off, and you can see when the concentrations flatline, this is when equilibrium is reached. So notice that the concentrations here are not equal to one another, rather they stop changing because the rate of the forward and the reverse reaction are equal to one another once you cross this line. Once the equilibrium is reached and the concentrations flatline, they stop changing or they become constant, we can say. If you were to start with only products, so some large amount of SO3, that SO3 is going to, those two molecules will combine with one another to form our reactants, so to speak. So the reaction's running from right to left instead. SO3's concentration decreases, SO2 and O2's concentrations increase, and we get the same equilibrium reached after a certain amount of time. All right, so now how do we quantify this? How can we determine what concentration of these reactants and products are present at equilibrium? We can quantify equilibrium with the equilibrium constant. So the equilibrium constant is given by a capital K. And this is why in this unit especially, the case of the letter makes a big difference. The lowercase k is the rate constant, which we saw in the first 3 lectures of this unit, the kinetics lectures. A capital K or an uppercase K here refers to the equilibrium constant. So often it's written as KEQ, but we'll see that different subscripts can be used. It won't always be EQ. Generally speaking, though, the capital K here refers to an equilibrium constant. An equilibrium constant is calculated by taking the concentration of the products over the concentration of the reactants. So it is always products over reactants. So this equilibrium constant here gives the ratio of products to reactants once equilibrium is reached, no matter the starting concentrations. I do want to note that this equilibrium constant is temperature dependent. A same reaction run at two different temperatures will have different KEQ constants, and we will investigate that further as we learn more about equilibrium. All right, so let's look at how the equilibrium constant shakes out mathematically. So going back to that original equation we were using, N2O4 to form 2NO2. Here we have five different experiments where we have different initial concentrations. So we can see we're varying. We're starting with high amounts of N2O4, and then we're slowly decreasing, or I guess I should say we're changing the amounts of N2O4 present, and we're also changing the amounts of the NO2 present. So here, these are the initial concentrations. We can see that we get different final concentrations, but what's important here is the ratio is the same. So no matter the starting concentrations or no matter the initial concentrations, we get approximately the same ratio. We get approximately the same ratio of products to reactants. And this is what the equilibrium constant defines. It is simply a mathematical ratio that relates the concentration of the products to the concentration of the reactants. And this ratio, this equilibrium constant, should be the same or approximately the same no matter the starting or initial concentration of the reactants and products for the reaction. So in all five of these trials, despite the different initial concentrations, we get an equilibrium constant right around 4.6, 4.63 times 10 to the negative third. All right, now how can we interpret the equilibrium constant? So again, KEQ, it's the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. So right away, whether or not KEQ is bigger than 1 or less than 1, you will immediately be able to tell whether the reaction is products favored or if it's reactants favored. If KEQ is bigger than 1, we can say that the equilibrium for that reaction is products favored. If KEQ is less than 1, we can say the equilibrium for that reaction is reactants favored. How can we say this? Well, just think about this in terms of basic math, right? If you've got a fraction where the numerator, the number on top, is bigger than the denominator, the number on the bottom, that fraction is going to be greater than 1, right? If I had, 3 over 2 or 4 over 3 or, 6 fourths or 10 eighths or whatever, if the number on top is bigger than the number on the bottom, when you divide those two numbers, you're going to get an answer that's bigger than 1. So if KEQ is bigger than 1, the top of the fraction must be bigger, which means there's more products. The products are favored. If your KEQ is less than 1, reactants are favored. Why? Again, think about it just in terms of basic fraction math. If I have a fraction where the number on the bottom is bigger than the number on the top, so 1/2 or 2/3, 3/4, and so on, all of those fractions, if you divide those values, 1/2 is 0.5, 3/4 is 0.75. When the number on the bottom is bigger and you divide those two numbers, you get an answer that's less than 1. So if KEQ is less than 1, we know then the number on the bottom must be bigger, meaning the concentration of the reactants is bigger, and we can say that reaction is reactants favored. So to real life examples, CO plus Cl2 to form COCl2. Here, KEQ is equal to 220. This is much bigger than 1, so we could say at equilibrium, this reaction is products favored, or we could also say that there must be more COCl2 at equilibrium than there is the two reactants. For this one down here, NH4SH to form NH3 and H2S, we see that KEQ is 1.20 times 10 to the negative fourth, much smaller than 1. So if it's much smaller than 1, we know that this reaction is reactants favored, or we could also say that there must be more NH4SH at equilibrium than there is the two products here. All right, next, expressing homogeneous equilibrium. In a homogeneous or homogeneous reaction, the reactants and products are all either in solution or in the gas phase. So remember, homogeneous meaning same. So think about what you learned in Gen Chem 1 with like a homogeneous mixture. That's a type of mixture where it looks the same to the eye, like tap water or, Gatorade or whatever, something that looks the same color all the way through. So a homogeneous reaction is one in which the reactants and products are all in the same phase. They are all either aqueous, they're in solution, or they will all be in the gas phase. All right, so for reactions in solution, we will often call our equilibrium constant Kc instead. Typically it's defined as Kc, where the little subscript C here refers to concentration. So if you have a reaction given here, A plus B forming C plus D, the lowercase letters are the coefficients. For reactions in solution, you define your equilibrium constant as Kc. So Kc equals the concentration of C raised to the power of the lowercase c here. So the stoichiometric coefficients become exponents in the equilibrium constant, times the concentration of D raised to the lowercase d power, the coefficient, divided by the concentration of A raised to the A power, the coefficient, times the concentration of B raised to the B power. For gas phase reactions, we typically use the subscript P, so Kp, P here meaning pressure, because these values, these concentrations, so to speak, are going to be expressed instead as partial pressures. So for the same reaction, if these were all gases, we would use a little lowercase p here, which indicates a partial pressure. So it'd be the partial pressure of C still raised to the power of its coefficient, times the partial pressure of D raised to its coefficient, divided by the partial pressure of A times the partial pressure of B. All right, so let's practice writing some case C expressions. We're going to look at 3 different reactions. We'll start with this first reaction. So I see that they are all in, well, obviously the question says it's Kc, but if I didn't know that, how would I know it's Kc? All 3 compounds here, or all 3 species in the reaction, are aqueous, meaning that they are dissolved in water, they're in solution. So I've got 2 products, 1 reactant. So for the first reaction here, I'll say Kc equals the concentration of I2 times the concentration of Ki divided by the concentration of Ki3. Note that all 3 species here all have coefficients of 1, and thus they all have exponents of 1, these unwritten ones here, in the case C expression. For our second reaction, I see that I've got 1 product and 2 reactants, so that 1 product should go on top. There we go. So Kc would be equal to the concentration of the product on top there, C2H2Br4, divided by the 2 reactants. So the concentration of C2H2 goes on the bottom, and the concentration of Br2 also goes on the bottom. Just note that Br2 has a coefficient of 2, and so it gets an exponent of 2 in the Kc expression. For our third and final reaction, you see that we once again have 1 product. So we would put CuNH3 2 plus up top there. You should include the charge within the brackets, because the brackets denote concentration. On the bottom, the concentration of Cu2 plus times the concentration of NH3. NH3 is raised to the 4th power because it has a coefficient of 4. Let's take a look at this for Kp expressions. So again, if I didn't know that I had to write Kp expressions, how would I know to do this? Note that in all the reactions I'm showing here, all of the species, they are in the gas phase. If they're all in the gas phase, you need to write a Kp expression. So for this first one, we would say Kp equals the pressure of CO2 times the pressure of H2 divided by the pressure of CO times the pressure of H2O. For the second compound, we can say that the pressure of SO2 squared times the pressure of O2 divided by the pressure of SO3 squared. Note that SO2 and SO3 have coefficients of 2, and thus they get exponents of 2. And last one, I'm going to challenge you to do on your own. All right. So let's look at how we can calculate Kp. So for this problem, I don't have the work on the slides here, but it should be fairly straightforward to follow. So for the reaction, 2NO2 forms N2O4. The concentration of NO2 measured at equilibrium was 0.016 molar, and the concentration of N2O4 at equilibrium was 0.042 molar. Calculate the value of Kc. All right, so what you want to do here is you want to start by writing a Kc expression. So I would say that Kc equals, and I would do the concentration of my product. So concentration of N2O4. Well, let's see. I do have the pen tool, so let me make use of this. Kc, and I apologize in advance for my terrible handwriting here. It would be the concentration of N2O4 over the concentration of NO2 squared. And then now all you need to do is plug in these values. I'll plug in 0.042 molar here and 0.016 molar here. And let's see what I would get as an answer. Let me grab my calculator just a moment. All right, when you plug these values in, the answer I get is somewhere around 164. You might round that down to 160 based on sig figs here, but 164. And I do also want to note that equilibrium constant values are unitless. They're just a mathematical ratio. You don't need to give them with units. All right, next, let's look at a Kp expression. After a mixture of hydrogen and nitrogen gases in a reaction vessel has reached equilibrium, the partial pressures of the gases are measured as 7.38 atmospheres H2, 2.46 atmospheres N2, and 0.166 atmospheres NH3. Calculate the value of Kp for the above reaction. Again, I don't have the work on the slide, but I will write it out here down below to help you follow along. So start by writing your Kp expression. So I would just put my lone product on top. So I would say pressure NH3 squared goes on top. And then on the bottom, I'll do pressure N2 times the pressure of H2. And the pressure of H2 needs to be cubed. That is a 3 down below there. Again, I'm sorry. My handwriting's not good, and I'm drawing on a touch screen laptop here. But hopefully you're able to at least generally make out what I'm trying to write there. So now I can plug my values in. I'll plug in 0.166 for NH3. I'll plug in 2.46 for N2 and 7.38 for H2. And let's see what we get. 0.166 for N2. 7.38 to the third power there for H2, and that's being multiplied by the pressure of N2. It's going to be a pretty small number. I get something around, we'll call this 2.79. 2.79 times 10 to the negative fifth. Let me write that one out. I got 2.79 times 10 to the negative fifth is my final answer here. All right, now let's have you try this one on your own. Finding partial pressure given Kp. For the reaction below, Kp equals 2.59 times 10 to the negative second, and here's your balanced chemical reaction. At equilibrium, the partial pressure of H2S was 0.557 atmospheres, and the partial pressure of S2 was 0.268 atmospheres. What was the partial pressure of H2 at equilibrium? So in this problem, you need to solve for the pressure of H2 instead. So go ahead, pause the video and see if you can find the correct answer here. All right, and hopefully you found a correct answer of 0.173 atmospheres. 0.173 atmospheres is the correct answer for H2. So real quick, I'm not going to show all of the work here, but you should start by writing a Kp expression. So Kp would be equal to the pressure of H2 squared times the pressure of S2, all divided by the pressure of H2S squared. And this is all equal to 2.59 times 10 to the negative second. So what you need to do here is rearrange this equation to solve for pressure H2. And again, you should get something around 0.173 atmospheres. All right, next let's look at the relationship between Kc and Kp. If we know the pressure, volume, and temperature of a gas, then we know the number of moles of a gas based on the ideal gas law covered in chapter 8 of the textbook we use if you need a little bit of review. PV equals nRT, pressure, volume, moles, ideal gas constant, and temperature. Now, if we know the number of moles in a given volume, then we know the concentration in molarity, right? Since molarity equals moles over liters, which we could define as N over V to put it in similar terms to the ideal gas law. So with this relationship, we can convert between gas pressure and concentration and thus relate Kp to Kc. So if I take the ideal gas law and solve it for pressure, I would get the pressure of a gas equals the number of moles of a gas times R times T divided by V. I'm going to isolate that N gas over V term. So I have N gas over V times RT. And right here, we just define molarity as N over V. And so I can make a substitution. And I'll pull out the N over V and just plug in concentration. So the pressure of a gas equals the concentration of that gas times R times T. Now what I'm showing here is how you can convert between a Kp and a Kc value. So start by writing a Kp value. So Kp equals the pressure of C times the pressure of D divided by the pressure of A times the pressure of B. So just using some generic reaction with reactants A and B and products C and D. Now what we're doing is we're taking this blue term right here, this pressure term, and we're plugging in this red term. So this red term is going in for this blue term in these spots right here. So you can see this goes in each of these 4 spots. So pressure C turns into the concentration of C times RT to the C power. And you do the same for D, A, and B. What you're able to do is because all 4 of these values all share an RT, you can pull out the concentrations. So what we're doing from this step to this step is the concentration values are being pulled out and the RT value is being kind of congregated and separated, because if we look closely here, these concentration values give us Kc. And so we get a final expression of Kp equals Kc times RT to the delta N value. Where does delta N come from? It comes from this right here. It's the sum of the coefficients. So delta N is the difference in moles of gas. It's products minus reactants. It's the number of moles of gas in the products minus the number of moles of gas in the reactants. All right, let's take a look at how we can convert between these two things. For the reaction, 2SO3 forms 2SO2 plus O2. The value of Kc equals 4.08 times 10 to the negative third at 1000 Kelvin. The problem asks you to calculate the value of Kp. All right, so our expression is Kp equals Kc times RT to the delta N power. You should be using the 0.08206 version here. So once again, in this unit, we now have 2 different equations that use the 2 different versions of the ideal gas constant. In the kinetics lecture, we saw the Arrhenius equation, which used the 8.314 version. Here, we're using the 0.08206 version. So again, make sure to keep those straight. All right, so we're being asked to solve for Kp. We are given Kc. R is a constant. We're given the temperature in Kelvin. Then we just need to solve for delta N. Remember that delta N is moles of gas. It's the difference in moles of gas between the products and the reactants. So in the products, I have 3 moles of gas, 2 plus 1. In the reactants, I have 2 moles of gas, so 2 plus 1 minus 2 equals 1. Delta N equals 1 here. There's 3 moles of gas in the products, 1 mole of gas, or 2 moles of gas, in the reactants. So the difference here is 1. So now you can just plug in your values and go. Plug this value in for Kc, plug this value in for R, this value in for T, and then this value gets plugged in for delta N, and you get an answer of around 0.335. And again, these K values are unitless. The Kc value is unitless, as will the Kp value. All right, let's look at a reverse problem. Here you're given a reaction 2NO plus O2 forms 2NO2. You are instead given the value of Kp. You're told the value of Kp is 1.48 times 10 to the fourth at 184 degrees Celsius. The problem asks you to calculate the value of Kc. So first thing I'm going to do is I'm going to take that equation and rearrange it to solve for Kc. So basically this entire term right here all gets divided from the right to the left side, and then I just flip the sides because I like my unknown on the left. So Kc equals Kp divided by RT delta N. Kp is given. The temperature is given. You just need to add 273 to that to get 457 Kelvin. And then we need to solve for delta N. Delta N here, again, is moles of gas in the products minus moles of gas in the reactants. I've got 2 moles of gas in the products. I've got 3 moles of gas in the reactants, so delta N here is -1. Now I can plug my values in. This goes in for Kp. This goes in for R. This value goes in for T. And this value goes in for delta N. Plug those numbers in and solve, and you should get an answer around 5.55 times 10 to the fifth. All right, I would like you to try this problem on your own. The equilibrium concentrations for the reaction between chlorine and carbon monoxide to form CoCl2 at 74 degrees Celsius are CO equals 0.012 molar, Cl2 equals 0.054 molar, and CoCl2 equals 0.14 molar. Calculate the equilibrium constants Kc and Kp. So real quick before you get started, you may be asking yourself, wait, you just said that a few slides ago that if they're all gases that I should write a Kp expression. And generally, yes, you should, but you can, in theory, also write Kc expressions for gases. You can express gases in terms of concentrations because they do have a mole amount and they do occupy a volume. So even though all 3 of these are gases, you are given concentration values. So the first step in your work here should be to write a Kc expression and then solve for Kc using these equilibrium concentrations given. Once you've done that, then you can use this equation along with the temperature given to calculate Kp. So go ahead, pause the video, take a few minutes, and see if you can come up with the correct answers here. Okay, the answers that I came up with for Kc, I found Kc to be around 220, and I found Kp to be around 7.7. So again, that's 220 for Kc and 7.7 for Kp. All right, now let's look at how we can express heterogeneous or heterogeneous equilibrium. So I pronounce this as heterogeneous. So heterogeneous equilibrium applies to reactions in which reactants and products, as you can probably guess, are in different phases. They are in different phases. So let's write the equilibrium expression Kc for this reaction. So we would write Kc equals the concentration of CaO times the concentration of CO2 divided by the concentration of CaCO3. But we need to stop here and ask ourselves a question. What is the concentration of a pure solid? Does this even really make sense? Can a solid have a concentration, right? Because concentrations, we typically think of something having a concentration because it doesn't occupy the full volume of the space it occupies, right? Like when we're talking about a gas, when we talk about a concentration of a gas, it's because, if you release, a gas into a chamber, a gas occupies some percentage, some amount of that volume is being occupied by the gas, so we can express that as a concentration. Or, if we're talking about liquids in solution, right? A solution of sodium chloride. The sodium chloride occupies some percentage of the space it's occupying. But solids, right? Solids, they do have a volume, but if we're talking about a concentration here, it doesn't really make sense because solids, they occupy the full space that they take up, right? That's kind of what a solid is. So solids don't really have concentrations, or to be more clear, we can kind of define the relative concentration for pure liquids and pure solids as being equal to 1. So again, because they occupy the full space, so to speak, if you get the analogy I'm kind of trying to draw here, the relative concentrations for pure liquids and pure solids is simply equal to 1. And so these terms are not included in the expression for the equilibrium constant K. So to be clear, anytime you see a species that has the state of matter symbol S or L, do not include that species in the equilibrium expression. Do not. Only compounds or species that are gases or aqueous in solution. Those are included in equilibrium expressions. All right, let's walk through a little practice writing Kc and Kp expressions for these heterogeneous equilibria. So I'll start with this first problem. I notice that my two products are both gases. I also notice that my only reactant is a solid. So when I go to write Kc here, I should say Kc equals N2O2 times H2O squared divided by 1. And so this would be that 1 on the bottom disappears. And so Kc here would simply be equal to N2O2 times H2O squared. You could also write a Kp expression for this since both products are gases. You could say Kp equals the pressure of N2O2 times the pressure of H2O squared. For the one down below here, I'm going to show you what the Kp looks like. So I see that I've got two reactants. I've got C solid copper and gaseous chlorine. And then my only product is also a solid. So if I write Kp, Kp would be equal to 1 divided by 1 times the pressure of Cl2. This simplifies to just Kp equals 1 over PCl2. So up here, I got rid of this 1 because the 1 was in the denominator and it wasn't necessary. Here, you do need to keep that 1, or at least this 1 from the CuCl2 needs to say, it needs to be 1 over PCl2. That 1 is kind of holding the value of the fraction here, and it is necessary. Again, you could write a Kc expression for this reaction at the bottom. It would just be Kc equals 1 over the concentration of Cl2. All right, let's do a little practice here, calculating Kp for these heterogeneous equilibria. Considering the following equilibrium at 295 Kelvin, NH4 HS solid forms NH3 gas and H2S gas. The partial pressure of each gas is 0.265 atmospheres. Calculate Kp for this reaction. Sorry about that. I was just checking. I didn't think I showed the work. I'll write this out real quick. So calculate Kp for this reaction. Kp would be equal to the pressure, sorry, that's a P, the pressure of NH3 times the pressure of H2S. And this would all be over 1 because NH4S is a solid. So now you can just plug your values in and go. So I'll just plug in 0.265 for both, and I get a Kp expression that should be somewhere around 0.0. Plug that in my calculator wrong. 0.0702 is what I got here for Kp. Sorry about that. I lost track of my mouse. Okay. So a summary of notes on K. The equilibrium expression at K has products in the numerator, reactants in the denominator. Reaction coefficients become exponents. So the stoichiometric coefficients become exponents. And again, important to note here that equilibrium constants do not have units. They are simply a mathematical ratio. If K is greater than 1, it's products favored, so the reaction can be thought as going to completion. If K is less than 1, the reactants are favored. The reaction hardly proceeds. K can be expressed in terms of molar concentrations, Kc, or partial pressures of gases, Kp. Pure solids and liquids are not included in the equilibrium expression for K. All right, and we're going to end today's lecture by looking at how we can manipulate KEQ values. We're going to look at three things: the effects of flipping a reaction, multiplying by a constant, and combining equations. Let's first look at the effect on KEQ of flipping a reaction. So if I have the reaction N2O4 forms 2NO2, my K value, and I'm just going to generally just use a K value here, but I could also call these KC since I am using brackets, which implies concentration. So K equals N2O2 squared divided by N2O4. What if I were to flip the reaction? So if I flip this reaction and reverse it and make it 2NO2 forms N2O4, my K expression, I'm going to call this K prime to represent a new reaction. K prime equals N2O4 over NO2 squared. You'll notice that this expression is the same as this, just flipped. So the new K value, or K prime, is equal to the original K value to the -1 power. So the conclusion here is that when a reaction is flipped, the new KEQ is the inverse of the original. Remember, that's what a value being raised to the -1 exponent implies, an inverse. So the new KEQ value is the inverse of the original. Next, let's look at what happens when we multiply a reaction. So using the same starting reaction, what if I were to take that reaction and multiply it by 1/2? So I get the reaction 1/2 N2O4 equals 1 NO2 instead of 2. My new K expression, K prime, would be equal to NO2 over N2O4 to the 1/2. I also notice that this new expression is equal to 1/2 of the, or I should say, the original expression raised to the 1/2 power, right? If I took this expression and raised it to the 1/2 power, I would be left with this expression down below. So I can say then that K prime equals the original K raised to the 1/2 power. The conclusion here, if reaction coefficients are multiplied by a constant, you need to raise KEQ to the same power. So if you multiply by 1/2, raise that K value to the 1/2. If I were to double the reaction, you would raise that K value to the second power. All right, and finally, let's look at the effect on KEQ of adding reactions. Suppose I had two reactions here. N2O4 forms 2NO2, and here's the K expression. I'll call this K1. Then I'll say 2NO2 forms 2NO plus O2. My second K expression is NO2 squared times O2 divided by NO2 squared. If I were to add these reactions together, I note that these two NO2s are kind of like an intermediate and they cancel each other out. So I'm left with N2O4 forms 2NO plus O2. My new K expression, if I were to just write a K expression based on this reaction, it would be NO squared times O2 divided by N2O4. You will notice here that when you add reactions, the KEQ for the resulting reaction is the product of the KEQ values for each reaction being added. If you took these two K values and multiplied them together, you would notice that we have NO2 squared on top, NO2 squared on the bottom. Those cancel each other out, leaving NO squared and O2 on top, and N2O4 on the bottom, which is the same expression we would generate if we were to just write it just looking at this equation. So again, the key conclusion here is that if you add reactions together, the KEQ for the new reaction is the product of the KEQ values for each reaction that you added together. So to summarize this, the K value for the reverse reaction equals the inverse of the original K value, or K to the -1. When reaction coefficients are multiplied through by some constant, the new K value equals the original K raised to that power. When two reactions are added, the K value of the new overall reaction equals the product of K values of the original reactions. All right, I'm going to show you real quick a little bit of practice on how we can manipulate and then interpret these values. So first question, you are given a chemical reaction here, and you're given a Kp value of 2.5 times 10 to the 10th power. Which is more stable, SO2 or SO3? So how do we answer this question? Which is more stable, SO2 or SO3? Let's start by looking at that K value. This is a very large K value, much larger than 1. And we should remember from earlier in the lecture that if K is greater than 1, that means the products are favored. This K value is way bigger than 1, so we know the products are going to be heavily favored here, which means that we would have a lot of SO3 at equilibrium. And if a lot of SO3 is being produced, it is fair to assume that SO3 is going to be more stable at equilibrium. Next couple questions here ask you to compute Kp for each of the following reactions, B, C, and D. These are all variations of the given reaction here. So I would encourage you to pause the video and go ahead and see if you can come up with the correct answers here for B, C, and D. And I will show the work on the following slides, but I think you should go ahead and see if you can try this and get the answers on your own. All right. So walking through the work, again, here is the explanation for letter A. Because K is so much bigger than 1, the products are favored, meaning SO3 is going to be the more stable species here. All right, now for each of these Kp reactions, let's start with letter B. So if I look at letter B, or reaction B looks like we took reaction A here and multiplied it by 1/2. I still have SO2 and O2 on the left side, and I've still got SO3 on the right side, but the coefficients have been halved from 2 to 1, from 1 to 1/2, from 2 to 1. So if the reaction's multiplied by 1/2, I need to take the Kp value and raise it by that coefficient, or by that value. So take that Kp value and raise it to an exponent of 1/2, and you get a Kp value of around 1.6 times 10 to the 5th. Letter C here, letter C, it looks like it's been multiplied through. So if you look at letter C, or reaction C, it's still the same, or we still have the same species on the correct sides. SO2 and O2 are on the left, SO3 is on the right, but it looks like it's been multiplied by 3/2, right? SO2 went from 2 to 3. O2 went from 1 to 3/2, that's the big giveaway. And SO3 also went from 2 to 3. So reaction C is the original reaction multiplied by 3/2. So you should take that Kp expression and raise it to the 3/2 power, and you would get an answer of around 4.0 times 10 to the 15th. Finally, letter D. Letter D looks like it's been flipped to me. SO3 was on the right up here. Now it's on the left down here. It also looks like the coefficients have been altered. The coefficients have been halved. So reaction D is reversed and multiplied by 1/2. So you need to do two things to it. The order here isn't going to really make a difference. If you had the half here and the -1 here, you should still get the same answer. I'll take that Kp expression, I'll raise it to the -1 power, and then raise it again to the 1/2 power. And I get the answer, 6.3 times 10 to the -6 for reaction D. So this is how you manipulate KEQ expressions. All right, here's a few more practice problems for you to try. So I would encourage you to try these on your own. Whoop, sorry about that. Let me back up here. All right, the answers are shown right here. So again, I would encourage you to pause the video and try these problems on your own, both letter A and letter B, and the answers are right here for you to check your work with. But that is the end of this lecture video. I hope you enjoyed and found it useful. As always, please feel free to reach out to me if you have any questions. I'll see you in the next one, and I hope you have a great day.